Welcome to the lecture series on numerical methods, and we are just discussing here this interpolation. In the interpolation, we have already discussed this finite difference operators like Newton's forward difference operator, backward difference operator, central difference operator, and after that we have covered up this unequal spaced interpolation like Lagrange interpolation and Newton's divided difference interpolation. So, today we will just discuss about this interpolation based on Hermite's hypothesis, that is Hermite's interpolation, and then we will just go for some of the examples that will be solved using Hermite's interpolation formula. So, whenever we are just going for this interpolation, basically we are just dealing here like if a function f of x is defined at the set of data points like x0, x1 to xn, and this function is approximated by a polynomial of degree n, suppose, since we have like defined points here x0, x1 to xn are the tabular points or the nodal points, and corresponding to each of these tabular points we have associated functional values like f of x0, x1, f of x1 up to xn, f of xn. Sometimes also we are just expressing this tabular points expression as in the form of x0, y0, x1, y1 up to xn, yn. Basically the idea is that we want to approximate this function f of x with a polynomial p of x. Since this function is satisfied at n plus 1 points, if you will just see, then we can just approximate this function with a polynomial of degree n here. Then if we will just use like Lagrange interpolating polynomial, then we are just using both this equally or unequally spaced interval points. Basically if you are just considering here x0, x1, x2 up to xn, sometimes maybe it is equally spaced, sometimes maybe it is unequally spaced, but for both these cases we can just apply Lagrange's interpolation formula. But here in Hermite's interpolation, so we can just extend this polynomial's degree, but at the same number of points. This means in Hermite's interpolation the degree of the polynomial is increased without increasing the number of tabular points here. This means it uses these functional values, that is f of x0, f of x1, f of x2, and this derivative, first order derivative at that points also. This means that it uses these functional values f of xi and f dash xi. So, I is varying from 0 to n here. So, definitely if we have here all the points 0, 1, 2 up to n, and f of xi is satisfied at n plus 1 points and f dash xi is satisfying at n plus 1 points, then we will have 2n plus 2 points here. And if you will just formulate a polynomial based on these 2n plus 2 points, then it can just generate a polynomial of a degree 2n plus 1 here. So, let us suppose y of x be a polynomial of degree suppose 2n plus 1. Suppose we are just considering here y of x is a polynomial of degree 2n plus 1. Since the polynomial involves here consists of 2n plus 2 points here. So, if you will just write this y of x is a polynomial of degree 2n plus 1, which approximates this function f of x here. Y of x is approximating this function f of x at the nodal points like x0, x1 to xn here. Then definitely we can just write this one as y of xi equals to f of xi and y dash of xi, this equals to f dash of xi for I equals to 0, 1, 2 up to n here. And if we want to express it in a polynomial form, we can just write this polynomial as y equals to summation I equals to 0 to n uix yi plus summation I equals to 0 to n vix yi dash, where uix and vix are polynomials of degree 2n plus 1 here. Definitely we can just say that where uix and vix are polynomial of degree 2n plus 1. So, if we want to express this as in a complete polynomial sense, this means that we are just using this n plus 1 nodal points to determine a polynomial of order 2n plus 1 here, since we have here n plus 1 points only. So, then we have to justify that whatever this polynomial we are just generating, it can take the n plus 1 points here, but it can produce a polynomial of a degree 2n plus 1 here. That is why we have to consider uix of polynomial degree 2n plus 1 and vix of polynomial degree 2n plus 1 also. So, if we are just writing here y of xi equals to f of xi and y dash of xi equals to f dash of xi, and the polynomial is expressed in the form of y of x equals to summation I equals to 0 to n uix yi plus summation I equals to 0 to n vix yi dash, which represents a polynomial of degree 2n plus 1. Then since we are just associating this polynomial in a Lagrangian sense, so that is why we can just consider that since usually we are just writing this polynomial y this equals to summation of I equals to 0 to n ui yi plus summation I equals to 0 to n vix, everywhere x is associated here. So, uix y of x vix and yi dash x here. So, we can just define ui of x this equals to 1 when x equals to xi, or we can just represent this one as ui of xj this equals to 1 for I equals to j, and this equals to 0 for I is not equals to j here. And similarly we can just define vi of xj this equals to 0 for all I and j here. So, similarly if we want to express also, since it is in a Lagrangian mode here and two functions we are just defining here, similarly we can just define that ui dash of xi, or we can just write this one as ui of or ui dash of xj this equals to 0 for all I and j, but vi dash of xj this can give you like 1 for I equals to j, and this equals to 0 for I is not equals to j here. Then we can just combine this Hermite interpolating polynomial in a 2n plus 1 degree sense that can generate a polynomial which can be represented is Hermite interpolating polynomial here. So, definitely if it represents a polynomial of degree n plus 1, then if we want to associate this one with the polynomial of degree n of Lagrangian interpolating polynomial, then we can just represent the polynomials of uix and vix as uix can be written as aix plus bi into lix square. Similarly, vix can be written as cix plus di li square of x here. This means that if we want to associate this Lagrangian polynomial with this variable here or this polynomial uix, and if we want to associate this Lagrangian polynomial Lix with this polynomial Vix, then we can just say that if it is multiplied here like Lix into Lix, then this can just generate a polynomial of degree 2n there, and if it is multiplied with this function here Aix plus Bi, so it can generate a polynomial of degree 2n plus 1 there. And similarly, since we are just considering Lix is the Lagrangian coefficient of Lagrangian interpolating polynomial, this Lix can be expressed in the form of like x minus x0, x minus x1 to x minus xi minus 1 into x minus xi plus 1 of 2x minus xn divided by xi minus x0, xi minus x1 of 2x xi minus xn. So, if we will just define this Lagrangian interpolating polynomial, where this Lix represents the coefficients of Lagrangian interpolating polynomial here. Using this Lagrangian interpolating polynomial, we can just determine these coefficients ai, bi, ci, di from these polynomials uix and vix here. So, if we will just write this Lagrangian interpolating polynomial here, the Lagrangian interpolating polynomial coefficient Lix can be written in the form of like x minus x0, x minus x1 up to x minus xi minus 1, x minus xi plus 1 up to x minus xn divided by xi minus x0, xi minus x1 up to xi minus xi minus 1, xi minus xi plus 1 up to xi minus xn here. Obviously, sometimes we are just expressing, as I have discussed in the earlier classes, that we can just express this one in the product form that can be represented as I equals to 0 to n phi of x divided by x minus xi into phi dash of xi here, where phi of x can be represented in the form of x minus x0, x minus x1 to x minus xn here, and phi dash of xi, especially this is called prime of phi of x. We can just write this one as d phi by dx at x equals to xi here. So, in both these forms it can be expressed since phi of x, it can also represented in the form of product of I equals to 0 to n x minus xi also, and some people are also using this one as prime of like product of I equals to 0 to n x minus xi also. So, if you will just express this Lix in different forms here by considering like n plus 1 points that represents a polynomial of degree n here, then if we will just take this differentiation of this ui dash, whatever we have just expressed for this Hermite interpolating polynomial, we can just write ui dash x as, since it can be expressed in the form of like ui of x is expressed in the form like aix plus bi lix square here. So, if you will just take the derivative with respect to x here, in the first coefficient we can just write this one as ai into li square x plus aix plus bi to lix into li dash of x here. So, if you will just take a common of this ai from both these terms here, we can just write this one as ai li square of x plus aix into 2 lix Li dash of x plus bi to Li of x, Li dash of x here. And if I will just take common here ai, since we want to separate or eliminate ai from these equations here. So, if I will just write this one, that can be written in the form of like Li square of x plus 2x Li of x, Li dash of x into ai plus bi into 2 Li x, Li dash of x here. So, likewise we can also differentiate also v of x, and we can just obtain this vi dash of x as, since vix is usually written in the form of like vix equals to cix plus di into lix square, and if you just take the derivative with respect to x here, this can be written in the form of ci into li square of x plus cix plus di into 2 lix into li dash of x here. And if you will just take common of ci from both these terms here, so ci into li square x plus x 2 li of x, li dash of x plus 2 li of x, li dash of x into di. So, if we will just put here x as xi, then we can just eliminate this ci di from both these equations, and we can get these coefficients, that is in the form of either in the form of lix or in the form of xi there. So, if we will just put this like the values here, this means that using like equations 3a and 3b here, that is as the conditions I have already written, ui of xj, this equals to 1 for I equals to j, and this equals to 0 for I is not equals to j, where for all I and j we can just say that vi of xj, this equals to 0 for all ij here. But we are just saying that ui dash of xj, this equals to 0 for all I and j, but we are just saying vi dash of xj, this equals to 1 for I equals to j, and this equals to 0 for I is not equals to j. If you will just use both these conditions in these two equations here, that is ui dash and vi dash, then easily we can just eliminate aix and vix here. So, now if you will just apply these conditions, then we can just find here. So, first condition we can just get as ai of xi plus bi, this equals to 1. Second condition we can just get as ci of xi plus di, this equals to 0. Since especially if we are just seeing here in the first term here, that is uix equals to aix plus bi into li square here. So, then if you will just put x equals to xi, then we will just get li square of xi, this equals to 1. But if you will just put in a like a vi of xi here or xj, both the terms we are just getting 0 there, since we have defined already that ui satisfies this Lagrangian polynomial or I equals to j coefficient only at x equals to xi points, but in the derivative sense if you will just consider, then vi will satisfy there. So, that is why we can just find this first coefficients as this form here, And if you just use this same coefficients for the second two equations like 6a and 6b equations here, then we can just obtain this one as 2xi li dash of xi plus 1 ai plus 2 li dash of xi bi, this equals to 0. Similarly, we can just get 2xi li dash of xi plus 1 into ci plus 2 li dash of xi into di, this equals to 1 here. Since now we have like 4 equations with 4 unknowns, so easily we can obtain these coefficients here. So first, if you will just try to eliminate ai and bi from these two equations here, then directly if you will just multiply simply, since this is a 2 li dash of xi is there, if you will just multiply here 2 li dash xi in this equation, and if you will just subtract, then we can obtain the coefficient for ai first. So if you will just multiply like ai xi into 2 li dash of xi bi, sorry, this is ai xi into multiplied by 2 li dash of xi plus we can just write bi into 2 li dash of xi into bi, this equals to 2 li dash of xi here. And this equation, it can be written in the form of like ai xi li dash of xi plus ai plus 2 li dash of xi bi, this equals to 0 here. So if you will just subtract, then this term will cancel it out, and this term also here cancel it out. So that is why we can just obtain ai as subtract, means we can just say that minus 2 li dash of xi here. And if you will just put this ai coefficient in the first equation here, then we can just obtain bi, and bi can be written in the form of like 1 plus 2 li dash of xi into xi here. Similarly, if you will just eliminate this ci and di from these two equations, like these two equations, we can just obtain cis1 and di as minus xi here. So just a simple multiplication if you will just do, then we can just find this coefficients ai and bi and ci and di from these 4 equations. So in a complete form, if you will just write this one, that it can be represented in the form of y of x equals to summation of I equals to 0 to n 1 minus 2 li dash of xi x minus xi into li square of x into yi plus summation of I equals to 0 to n x minus xi into li square of x here into yi dash. This is the complete formula. Sometimes also you can just remember these coefficients as hix here, this one is hi dash of x also here. Since li square x is easy to remember here, and both these coefficients, first one is multiplied, since we want to generate this polynomial of degree 2n plus 1 here. So that is why yi can be multiplied there and yi dash can be multiplied here over. And the beauty of this method is that only n plus 1 points are used to get a polynomial of order 2n plus 1 here. And if we want to find this error terms here, the error terms can be written order of 2n plus 1 here, that is, since this polynomial is involved here, the degree of 2n plus 1 here, the error term will be just represented as f to the power 2n plus 2 zeta by 2n plus 2 factorial into product of x minus xi square here. Since if you will just see here, so both these polynomials that has been multiplied here, so that is why if you will just consider like the earlier Lagrange interpolation error term, we are just used to write like f to the power n plus 1 zeta by n plus 1 factorial into product of like x minus xi there. So if Li square of x, if we are just considering, so it can be taken as the square sense there, and the derivative can be taken as the order of 2n plus 2 here. So based on this, if you will just go for a problem here, that is suppose if the question is asked like using Hermite interpolation formula, find the value of sine of 0.5 from the following data. So we can just write first like Li of x0, sorry, L1 of L0 of x0, L1 of x1, L2 of x2, then we can just find their derivatives and you can just put in the formula, then you can just obtain this interpolation in that problem. So if this problem is given like sin x data is just given and it is asked to find sine of 0.5 here. So suppose these tabular values are given as x sin x cos x here, and the values are like minus 1, 0, 1 and like minus 0.8415, this is 0 and 1 value is 0.8415 here. Similarly cos values are like 0.5403, cos 0 is 1, then this value is also 0.5403 here. And we have here, if you will just see, f of x is sin x, f dash x is your cos x here. And if we want to express this one in the formula like here y of x, if we want to find, so directly we can just put y of xi or y of xi as f of xi, that is sin of xi here, and if we want to put yi dash of xi here, so that can be written as cos of xi there. So first we have to find here like L0x we will just find. So if we want to find here L0x first, L0x can be written in the form of like x minus x1, x minus x2 by x0 minus x1, x0 minus x2 here. Similarly L1x can be written as x minus x0, x minus x2 by x1 minus x0, x1 minus x2 here, and L2x can also be written as x minus x0, x minus x1 divided by x2 minus x0, x2 minus x1 here. So if you just put these values here like L0 of x here, it can be written as first value like here 0 it is there, so x into x minus 1 divided by, so x0 is like minus 1 here, so minus 1 minus 0, then like minus 1 minus 1, so minus 2 it is there, so definitely this is minus minus, so that is why it will come as 2 here. Similarly if you will just determine L1 of x here, that can be written as like x minus of minus 1, so x plus 1 into x minus 1 here divided by, if you will just see here, since we have these coefficients like x0 equals to this one, x1 equals to this one, x2 equals to this one here. So we can just write this one as like minus of x plus 1 by x minus 1 divided by 1, it will just come. So similarly you can just obtain like L2x, that is x minus x0. So that is how you can just write x plus 1, then x minus 0, this means that x only. So divided by, if you just see, this will come as 2 here. So directly we can just put the values there, like L0 of 0.5 if we will just put here, then we can just obtain this value as minus 0.125, and L2 of 0.5 if we will just put, we can just get this one as like 0.75, and if you will just put these values of 0.5 here, then we can just obtain these values as 0.375. So similarly we can just obtain like a L0 dash of x, that is directly if you will just differentiate here, since this is the polynomial we are just getting here. So L0 dash x we can just write as 2x minus 1 divided by 2 here, and L0 dash of 1 if we want to find, so we can, sorry, minus 1 here, since we have the points like minus 1 here, we can just obtain that one as a minus 3 by 2 there. So then again if L1 dash of 0 if we want to find, that can be written as 0, then L2 dash of 1 if we will just find, that will be represented as 3 by 2 here. So finally if you will just put these values, then we can just get this value as 0.4794 here. Therefore y of 0.5 we can just write it as 0.4794, and the exact value of sin 0.5 it can be represented as 0.4794. If the Lagrange's formula can be used, we get sin of 0.5 as 0.4207, but for the higher degree polynomial it can just provide a better result. Thank you for listening this lecture.